tomorrow, just to give you an idea, because this fits this topic. So when we go to the lab tomorrow, you're going to see me actually. We'll do it frictionless, and we'll do some with friction. But we're going to have a table. That's like a table. And we're going to have a cart on the table. A cart's going to sit on this device, which is frictionless. We bought these actually fancy stuff there. There's a pulley here. There's a string attached to this. It will never be 100% frictionless, but we'll pretend it's frictionless. And we're going to attach a little weight there. And the minute you put that weight there, that cart's going to slide down. Let's say the mass of this is 0.7 kilogram, and the mass of this is 0.2 kilogram. If it is frictionless, the minute you attach that weight, that thing will go down. It will move down. And since it will move down, so this is frictionless, no friction. The fact is no friction, it will move. And which way is it going to move? Think about it. If it's going to move, this piece is going to move which way? Down. And the top one is going to move which way? To the right. That's the only option. It's not going to go backward. There's no incline on the table. Why should it go backward? So it's going to move down, that little weight, and the bigger weight is going to move to the right. So we'll move, question number 1, find the acceleration. And question number 2, find the tension in the string. It will be the same tension. Now again, if you think about this one, the one sitting up there, the only reason it's going to move to the right is why? Because the string is pulling on it to the right. So that string, the tension in it, is going to be in that direction. It has to be, to move it to the right. That means the tension in this one has to be upward. For every action, there's an equal and opposite reaction. So this is the same string. If you stretch it out, if you just skip the pulley and make them straight, this is going this way. That means equal and opposite value. This has to be going backward with the same value. So how do we find what t is, and how do we find the acceleration? We're going to do a free body diagram for each one and try to write some equations. Now you're looking at that one. We have the weight down. So it's 1.96. 0.2 times 9.8, 1.96. So let's look at that one, just the first one. This is the 0.2 kilogram. It is moving, it has a weight down of 1.96. It has the tension going which way? Up. And they are not equal to each other. Why? It's going to move, because initially it's not moving, so it's going to start to move, so there will be some acceleration. This is going to move. It's going to move in this direction. If it's moving down, that says, you know what? This force might be bigger than that to move down, because if this was bigger, it will move which way? Upward. So the net force, F net, equals mass times acceleration. The net force is the 1.96 minus t. equals the mass, which is 0.2, times the acceleration. You're going to be doing something like this tomorrow in the lab. So if you look at that equation, 1.96 minus t equals what? 0.2 times a. If you move the minus t to that side, 1.96 equals what? 0.2a plus t. How many equations, how many unknowns in that equation? 2. Can't solve it. Let's look at the 0.7 kilogram, the glider on the top there. Let's write all the forces on it. What do we have for forces? We have the weight down, which is mass times gravity. And that number is 6.86. The glider is not bouncing on the table. It's not going up and down on the table. So that means we have a normal force upward there. And that normal force has to equal to this. There is no net forces in that direction, because if there is one, then we're going up in air, coming down through the table. And we have the cable pulling in that direction, T. And which way we're going to move? It's going to move to the right. So what is the net force in the direction that you're moving? What is the net force? The longer you wait, the longer we stay. I'm in no rush. Jimbo. How are you? Good. What do we have for a net force? What are the forces in the x direction? Yes, Emily.
Is it just T?
Yes. F net. It's only T in that direction, which equals mass times acceleration. So T equals, what's the mass? 0.7 times A. That's my second equation. There is no other forces in the x direction. I don't have any friction. No friction, the problem says. So now I get two equations by two unknowns. We go to the math, we try to solve them. We use substitution. I already know what T equals to. So 1.96 equals 0.2 times A plus, in place of T, I'm going to write what? 0.7 times A. .96 divided by 0.9, 2.18. And if we know the acceleration, can we find the tension? The tension is what? 0.7 times A. 0.7 times 2.18, which is 1.52 Newton. When we do this in the lab tomorrow, we'll be able to calculate the acceleration from the math there. Then we're going to run the experiment and see if the acceleration agrees with us, if we get that number. And maybe we'll change the weight. We put a different weight here instead of 0.2 kilogram, do another 0.4 and see what will happen to the acceleration. that acceleration should become larger. The more weight you put, the faster it's going to move. If you put a 10 kilogram, nothing will fly. So that's connected surfaces or connected objects. Let's try another one. Pick an angle, a value for the angle. What do you want to use? Any number. A reasonable number. 60 degrees? Oh, this is 60. Okay. Let's put a mass here again. And let's say it's frictionless. No friction again. This problem, no friction. Let's take a mass. How much? Pick a number. Any number you want to. Come on, somebody pick a number. What is it? 20. 20 kilogram. And here's a pulley. We're going to attach a string to that. Dangle it over the pulley. It's going to come out this end. And I'm going to put another mass, hang one here. Let's say I'm going to put 18 kilogram here. Now the question, I have multiple questions. Will the system move? If yes, and I can tell you till I do the math. If yes, find the direction, which way is it going to move. Find the acceleration and find the tension in the cable. Remember, these cables, this is pulling up this way and this is pulling back that way. Now I'm going to redraw that picture and just put numbers on it so to see if it's going to move or not. I'll make this object right there. That's the 20 kilogram. It has a normal in this direction, perpendicular to the surface. It has the tension in the cable. And we have the weight. But I'm going to take the weight and break it down. Break it down to an X component and a Y component. A component in this direction and a component in this direction. The component in this direction is mg sine theta. The component in this direction, mg cosine theta. Theta is 60. M is what? 20. So let's do the math. 20 times 9.8 times sine of 60. I got 169.7. About 170. Let's look at this one here. That little weight, 18 kilogram. What do we have acting on it? We have the weight up there. That's the tension. And we have the weight down. This is dead too. The weight is mass times gravity. What's the mass here for this one? 18. And gravity is 9.8. What's 18 times 9.8? 18 times 9.8, 176.4. Which way is it going to move? The only places you have to look, you look at this number and you look at that number. Which one is bigger? So this is going to go down, it's going to move this way. If they are equal, it's not going to move. Since this is bigger than that, this is going to go down and this is going to move up. If this number was bigger than this, it will move down and that will move up. That's how you know which way it's going to move. If they are equal, you're not going to move. So let's look at that one again. Free body diagram for each one. Find out the direction that you're moving. So that 18 kilogram we have the weight down, which is 176.4. We have the tension up. It's moving this way. The fact I'm moving down, I'm going to say F net equals mass times acceleration. My F net, since up and down, is this force minus that. Equals 18 times A. That's one equation. The second one, let's look at the top one. That's a 20 kilogram. I'm just turning it sideways. I have T going this way. I have what? 170 going back. I have N going up. And I didn't even calculate this because there's no friction, but if you want to calculate that, that's 20 times 9.8 times cosine 60. That's a 98 here, which means that's a 98. That thing is not going up and down in this direction. And it's moving in this direction. Moving to the right. So all I care about now, what is the net force in the x direction? Because you're moving to the right. My net force, since I'm going to the right, is T minus the 170 equals the mass, which is 20 times the acceleration. And now notice I got how many equations by how many unknowns? 2 equations by 2 unknowns. So let's take the 2 equations, solve them. That's one of them. Now, if I move this one here, if I solve it for t, I get t equals what? 170 plus 20a. You come back here and plug it in. 176.4 minus t, which is what? 170 plus 20a. $176.4 minus 170 minus 20a equals 18a. 6.4 minus 20a. Add 20a to both sides. What's a equal to? 6.4 divided by 38.17. 168. If I know the acceleration, can I find the tension? Sure. Grab one of these equations. I can grab that top one. Tension equals what? 170 plus 20 times A. 170 plus 20 times 0.17. $173 Newton. That's what the tension in the string. There's only one topic left in this chapter, and that's actually, I'll put it with the same video, is circular motion, when things are going in a circle. So I'll just add them to this video. I'll label this as connected object and circular motions. That's an M, looks like an H, motion. When you're on the merry-go-round, going around there on the merry-go-round, there's a force pointing toward the center, is called FC, Centripetal Force. Our book calls it CP, Centripetal, center seeking. That's what the CP stands for. Centripetal force. Well, first we found out that the centripetal acceleration, when things are going in a circle, there is an acceleration called centripetal acceleration, and the value of that is v squared divided by r. And since Newton says, well, the force is equal to mass times acceleration, then the centripetal force is equal to mass times v squared over r. mv squared over r. What is that ride, a Six Flag that you sit like in, it looks like a swing, but I start to spin, everyone moves to the outside. Tamaha? Okay, that, it looks like this, people sitting, but as I start to swing, like you're dangling like this, right? Each one is sitting straight like this. But as I start to spin, you'll see these wheels go like this. I mean these, right? You start to spread to the outside. Why? Because if you move in a circular path, there's a force pushing you in that direction. And the value of that force is mv squared over r. If we know what the radius of that wheel is, we know the velocity of that and the mass, we can tell you what the value of that force is. So that's the reason why you go to the outside. So let's take an example. Somebody has a mass of 80 kilogram, again, about 176 pounds. Velocity, this one was spinning at a speed of 10 meters per second, good speed. Radius of that, I don't know, 5 meters. There's a force actually pushing on you equal to the centripetal force. Centripetal force always toward the center. The value of that force pushing you out to float, what's the value? Is going to be m times v squared over r. So the mass is what? 80. Velocity is 10. Square it, then divided by r, which is 5. I think that's 1600 Newton. Now, the movie with Tom Hanks, Apollo, was it 13 or 16? 13? Apollo 13, that movie. They have a lot of scene in that movie where you have frictionless. Tom Hanks is floating there. Well, you feel that on the moon. How do they video that? How do they get these videos to show these guys floating in the air? That wasn't fake. That was real, actually. They were floating.
Isn't there like some kind of airplane that goes up?
Yes. The Air Force has a plane called the Comet Vomit. It's a 747. They stripped all the seats out of it, and it goes in a circle like this. So what happens when you're on the top of that, if you make sure, if you're on the top of that, and somebody got to figure that, we know what the speed of the plane. Let's say the plane is going at 400 miles per hour. What's 400 miles per hour? How many meters per second? Divided by 2.24. 178, 180, so roughly 180 meters per second. The plane's flying at 400 miles per hour. Now, when you're on top of that, to create zero gravity on the top, because you got your weight down, the weight, which is mass times gravity, and you also got that centripetal force, the value of that centripetal force pushing upward of mv squared over r. That's what's going to happen. So when you're at the top, if you want to create zero gravity, you want to make sure what? That these forces are equal to each other. Nobody's pulling on you, and that's why you float. So if you set them equal to each other, notice the mass becomes no factor. We don't care how much the plane weighs, who's in the plane, how many people, that doesn't matter. They cancel each other out. You get the velocity squared over r equals to g. So before they go up there, they know what the speed is. The next thing, they got to calculate what the radius of that turn. So they keep going. So what's r should be? Let's do the math. V is 180 miles per hour. Square that one. Divided by r equals 9.8. (180 squared equals 9.8 r). What's 180 when you square it? 32400 equals 9.8 R. We need that to be 3306 meters, the radius. That's approximately 3,700 yards. So the radius of that mile, I think about 1,700. So about 2 mile radius. So you go like this, and next one you do it again, and you do it again. So for that time, from here to there, you get zero gravity. Then it's gone. You get ready for the next C, and then as you do it again, you get zero gravity again, and zero gravity. So you get to have 10, 15 seconds in each one where you have zero gravity. And that's how you videotape that. Now, if you stay on that plane, the plane continues to go in a circular pattern like this. When you get the bottom here, what's going to happen is your weight is down, and what? mv squared over r is down. And if they are equal to each other, if you add them, you have 2g acting on your body. You're stuck to that seat. You're not going anywhere. You feel like a bigger force pulling on you. It's like somebody your size just sat on top of you. That's what it feels like it right there. Because now you have twice gravity pulling on you. When you're right here, you get the weight down, and you get mv squared that way. So if there's a problem, something broke there, let's say the door went open and you got sucked out, you're actually going to go in that direction because of these components. You have a component in this direction, a component in that direction. That's the direction you go flying. So at any point on that pattern, the value is changing. When you're right here, your weight is down like this, straight down, and that value in that direction. So you can see the force acting on you at any given point is really different than any other point on that pattern. We use this logic, by the way, for cars. Meaning what? When you actually, in a car, you make a tight turn. If you're going really fast, let's say this is 100 meter here, the radius, and you're in the car here and try to make that turn. Come back here. You're going to go around the track here. So when you're right on the track here, on that circular path, there's a force pushing you in that direction of mv squared over r. And if the car has a mass of 500 kilogram, then the value of that force, which is 500 times your speed, let's say you're going 65 miles per hour, and if we change 65 miles per hour to meters per second, it's 29 meters per second. Divided by what? 100. And it's 4205. That's the force. Now, what's going to happen to you as you make that turn? Well, we don't know. It depends on what kind of tires you have on your car, the surface of the road, because you have a force in this direction of 4205 pushing you in that direction. What's keeping you from sliding out, if anything? It's the friction force between the tire on the road. That's what's keeping you. If you have good tires, good surface there, you'll stay on the track. If you got really tires that's already gone, smooth, there's no tread left on them, the road is wet, you're not staying on that track. You will go sliding to the outside. So when you watch car racing, you go, well, that's a problem. Car Daytona, you see the cars going like 200 miles per hour. That track is not that big. That radius is not that big. There's no way you're going to stay on the track. So what do? We need an extra force to keep you on the track. The track will look like this on Daytona, on these turns. Has a steep angle. Why? Because now, this is the mv squared over r, pushing you out. This is the friction force, pushing you back in. That's not enough to keep you on the track. By bending the road like this, by making it an incline, you also get m times g times sine theta here added to that value on the track. And that will give you addition to that force to keep you on the track. So if you see some like sharp turns, even local ones, a lot of times the road is bent, has a little angle with it to make sure you stay on the track. But that's all I'm going to talk about centripetal force there, because we have a whole chapter on things going in a circle there when we get to it. But you might see a couple of problems about this equation, mv squared over r. That's actually the centripetal force.